Hello everyone, I'm David and this is Kuba. We're students at AGH University of Science and Technology, and we're also developers. I work as a Scala developer in the telco industry, and Kuba is a creative designer in the games industry. And we'll be talking about our success story with Scala in a scientific setting, particularly in a high-performance computing environment, by which I mean a top 500 supercomputer. And if there is one thing that we want you to take from this talk before you head off to lunch, is that Scala is perfectly viable for research, particularly with Akka and the ways you can really distribute your scientific logic into such a cluster. But let's take a step back in history to a year ago. We are attending a course on systems modeling and simulation, which was led by Dr. Dworak, who's present here in the audience. And one thing that you have to know about him is that he's very keen on Erlang. And, well, he proposed a project to run a simulation about, in large scale, about quite small but complex creatures called the foraminifera. And as a Scala developer, I felt that it was my duty to challenge him with a Scala implementation of this project. So we ran two projects simultaneously. Kuba helped me with this, and we had a set of goals that we wanted to achieve with this project. We really wanted to run on a high-performance computing platform, because that was probably our only chance to do this in our student's lifetime. And we also wanted to hit a grid size of order of 9, because the previous research that we found with similarly complex creatures was on around order of 5 cells. So we wanted to be so much better than the previous people who did this. And we wanted to manage concurrency with actors by splitting the grid and having worker actors perform computations over a part of a grid. Then we wanted to distribute such actor model over a cluster. And also introduce some desynchronization mechanisms that would allow us to perform even better in such setting. And most of all, we wanted to do better than the Erlang group. Well, it's not that we don't like Erlang. I actually work in the telco industry, so I have some professional experience with Erlang as well. And it's a beautifully designed language, but it has very specific design goals. And these goals are not exactly CPU-intensive computation over a large in-memory data set, especially when single node performance is also very important. So we decided that we're going to use Scala and show who's the better in this. So in a true student spirit, we took a very lazy approach where we could really drop out at any point and say that we just want to pass the course, and started with a very minimal viable implementation. And that implementation was a single actor in an actor system. And this actor only sent a message to himself whenever he finished an iteration. So this was obviously a single node implementation. It was highly sequential. We only had a single biological model implemented, which was the foraminifera. But we managed to achieve our first goal for the further steps, which was the signal propagation algorithm that Kuba will elaborate on further. But the main thing that you need to know at this point is that it allowed us to reduce the complexity of making a decision for each cell, because we only had to traverse the grid once per each iteration, since all the information about the environment was already in the cell. And we ran this on an order of 5 cells, which was basically replicating the previous results for similar models. And our main design decision at this point was to use Scala. And this decision was, had two major contributions. The first one was to use the JVM, which has well-known performance characteristics. The JIT is a masterpiece in its own, and we know it well. And the platform itself provides enterprise-grade tools for monitoring, profiling, and deployment of any apps. It's so widely used in the industry that it was very easy for us to find hot paths, to do micro-benchmarking, basically do anything that you want when you want to create a highly performant app. And on top of that, we wanted to use Scala. And for Scala, the name says it all. It's a language for scalable programming. But one of its biggest advantages is that it's the mix of functional and object-oriented programming is very expressive, and it's also a very general language, in the sense that you can make a proof with Scala, you can do type-level computation, you can write your general business logic, you can write a DSL, like in Spark, and obviously this power comes with a great responsibility, but in the hands of a proficient programmer, it can be extremely efficient. And especially when it comes to concurrency, whatever level of abstraction you pick, whether it's parallel collections, futures, promises, tasks, streams, actors, there's always a way to decompose your logic from the execution and sensibly reason about it. And it's also multi-platform, so any code you write purely in Scala can be taken to the native environment with Scala native, and also can be taken to the JavaScript environment with Scala.js. And if you want to explore more about the JS part, you should look up the U- framework. That's something that we developed at my current company. And it leverages Scala on the backend and Scala.js on the frontend for a single, seamless, type-safe environment for development of web apps. So if you're interested in that, then that's surely something that you should look up. And also, the second most important point from this presentation is the Ryan Gold's link. Also loves Scala, and there's much more under this link if you want to look it up. Okay, but coming back to the simulation, we decided that we're not so lazy after all, and we can do a concurrent computation for this. So we implemented a way to split the grid and then make the workers inform their neighbors whenever they would finish an iteration. And at this point, they would just send the result of the whole result of the iteration to the other worker. So he could just apply the changes that related to him as soon as he got the message. And this was running in concurrent. It was desynchronized in the sense that whenever a worker got full information from his neighbors, he could start the next iteration. And it made us implement conflict resolution because it was highly possible that the units migrating from one part of a grid to another would collide. And it also was the same for the signal values. And this, we were able to run this on an order of 6 cells, which was already an improvement. But once we took a look at the mechanisms that are available there in Akka, it made sense to take it to the distributed world. So we use the Akka Cluster sharding mechanism, which is a very simple way when you just have some workers to put them into shards and let Akka manage these shards, migrate them between nodes, spin off actors on the nodes in a way that's transparent to your logic. And using this, we made our computation basically from concurrent implementation to distributed implementation took us a day. And the only thing that we had to implement was custom serialization because we know how well JVM does with this. And also we had to reduce the protocol a little bit to make sure that we only send the information that's relevant to a worker and not the whole grid because we didn't need that. And when we were only in a single JVM, we didn't need to worry about that because it was shared memory. And this allowed us to hit our goal of order of 9 cells. But just a few words about the cluster sharding mechanism that we used. It's really simple to implement. That's basically the whole implementation that we need to do. There are just a few functions. One resolves the shards, and the other resolves the worker IDs. And you tell the cluster sharding mechanism how to spin off new actors, and then you receive the single reference to such a region. And for the actors within that region, it's completely transparent. They can reply to each other. The shards will migrate between nodes. And it also works with Akka persistence. So if you want to do something that's more failure tolerant than we did at this point, then that's possible. And that was the point where we decided that maybe it shouldn't only be a master's thesis. Maybe we could do a research paper and not do a master's thesis at all. Which is the lazier way to do it. At AGH, you can actually graduate by defending a research paper instead of a master's thesis. So since it's shorter, it only made sense, right? We decomposed our model from the execution logic. So now when you define your cell types and their behavior, you can just run in the cluster. There are ways to gather the metrics. There are ways of post-processing these metrics. We gather performance metrics at all levels of the stack. And all the conflict resolution and signal emission mechanisms that we did it's possible to statically reconfigure them with code, but it's also possible to reconfigure them at runtime. And in around 2 months, we hope to open source this. So if you follow me on GitHub, it will make sure to let you know when it's done. We're mostly working on documentation, and we want to make the synchronization part more configurable. Some of the results from the paper that we're working on, for strong scaling, we had fixed grid size, which was order of 7, and that's around 300 gigabytes, 3 nodes on Prometheus, which is the supercomputer here in Krakow. And we're able to reduce the average computation time from 8 hours and 22 minutes to 11 minutes. But that doesn't tell you how much overhead we were introducing. So we also did the weak scaling experiment. And we had a fixed problem size per core here. And even though the solution time increased by 44%, the grid size was increased to 14,000% more. So we believe that this is a good result, taking into account how much communication there had to be between the nodes. And we hope to improve that result even more once we make the synchronization part more configurable. So we would allow the workers to maybe wait 3 or even more iterations before they actually have to apply changes from their neighbors. And the mic is yours.
Okay, so the mic is mine, but unfortunately I've got only 5 minutes, and I thought that I've got about 12. So let's go straight to the implementation. I'll do my best to do as short as possible. So we implemented a few mechanisms that I think make our framework special. The first mechanism is signal propagation. We are basing on the smell propagation model from the article at the bottom of this slide, dynamic assignment of tasks to mobile robots in presence of obstacles. And how it works. Any unit in the grid can emit the signal. The signal is propagated in each iteration to the whole grid. It means that if all units are emitting the signal and it's propagated in the whole grid, the single unit can base it only on his own state to predict where are other units and additionally where are the tasks. The second mechanism is buffer zone. The buffer zone is basically like this picture on the right, 2 workers, and they're communicating between each other by this buffer. So we can make an analogy, like we've got 2 islands, and 2 islands with different government and different law, and the guys from one island want to migrate to the other zone. If they are migrating, they're using the boat, so the buffer zone, and they are traveling to another worker zone. Then there, they've got different law, different governments, so they have to they have to settle down there, and it depends on the worker, the gray one, what he'll do with this thing. So we've got the third mechanism, conflict resolution. Conflict resolution is the special mechanism that allows the worker who retrieves the information about the buffer zone, what to do with this and how apply the changes. As we can see on the left, we've got the pseudocode of example of conflict resolution for foraminifera habitat simulation, as David mentioned before. Foraminifera are small single-celled creatures, and we've got the pseudocode for 3 cases. When foraminifera is migrating to our buffer, to our zone, and it meets in the destination cell another foraminifera, we provided a small mechanism like cannibalism. One foraminifera eats another and growing in energy. The second case is when foraminifera meets empty cell. It's pretty easy, it's just migrating. And the third case is when foraminifera meets the algae, then it consumes it and grows in energy. Our config resolution is pretty easy to implement by the user because it has Scala's strong type system, of course. It's fully customizable and configurable on runtime, so he can provide his own strategies and implement this, and of course swap during the simulation, and it should still work. Then the pattern mechanism, pattern matching mechanism. Scala is pretty easy to implement this. It's nice looking, and additionally, we are assured that we covered all possible cases in our simulation. So let's go to experiments, because when we get parallelization, we've got, of course, process of this, but also cons, so the drawbacks. And the drawback is that the result of the simulation can have errors or something like this. And we had to check if the parallelization have any major impact on our results from the simulation. So, first specimen was to take foraminifera habitat simulation and implement this. It was nice because we had multiple papers and previous research, but unfortunately we are not biologists, so we needed something similar, but a little bit simpler. So we've decided to make our simpler version foraminifera habitat simulation. It's rather like predator-prey, rabbits and lettuce simulation. On the left, we've got our first 150 iterations of the simulation for single core, one worker. The green ones are algae, the brown ones are foraminifera. And as we can see, after the first state, they are crystallized and then pulsing. It's pretty characteristic for predator-prey algorithms. On the right, we've got our main configuration values. And of course, user can specify his own configuration. At the bottom, we've got the table of 4 experiments that we've done for 4 different cases of foraminifera simulation. Experiments. Here we've got 4 charts for our experiments. The main aim was to prove that we've got no major impact of the parallelization. So 2 charts on the left are the most important ones because the lines are overlapping. So it means that we don't have any errors. Those on the right, it's like, what? Because we've got a lot of lines and it's really big mess. But trust me, it's pretty common for a predator-prey and Lotka-Volterra model that populations are oscillating and the populations are balanced. What was really important for us, because we wanted to make performance experiments, and they are really long-term. So we wanted to be assured that our populations won't extinct. What's next? So for the future plans, we'd like to extend our buffer zones. What's implicating the configurable desynchronization. We'd like to allow our user to specify his own desynchronization and where is the limit of it. What's more, smart hashing function for cluster sharding mechanism to make our communicating between nodes even better. And I guess that's all. Thank you very much for your attention, and maybe do you have any questions? And you can, of course, catch up with us later and ask anything what you want. Thank you.
So, one question, please. Anyone?
Thank you very much. You're probably familiar with the Conway's Game of Life, which is a tiny set of rules that produces very much of complexity, but what is very interesting about it, that it sometimes produces like repeating patterns of life and death of cells. Did you manage to see this kind of patterns in your much larger scale simulations or no?
Well, later in our work, we're working on much larger scale, so we're not really looking at any visualizations. But on the smaller scale, some patterns really repeat, and you can really see, as Kuba mentioned on the smaller animation, that they oscillate in very specific patterns, and you can see waves where they move across the whole grid. So it would be pretty interesting to see what patterns we could visualize on this.
Yeah, we've made up to 5,000 iterations visualization, and yeah, they had a behavior characteristic for the life and death cycle. Yeah, we mentioned that.